Swayam Prabha. Digital India. Educated India.
Hello students, welcome to today's lecture. In last few classes we have been discussing principles and postulates of quantum mechanics. So far we have discussed two postulates of quantum mechanics, and we will continue our discussion by reviewing the two postulates that we already have discussed and then carry forward our discussion. The two postulates that we have discussed so far, they kind of set the ground for our future discussion. For example, postulate 1 promised us that if we want to treat any system quantum mechanically, the quantity that we must always be looking for is the so called state function or the wave function that we denote by a term psi, the function psi. This state function completely specifies the state of the system. That means everything that we possibly can know about the system is out there in this state function psi, but the wave function itself does not have any physical meaning. However, what has a physical meaning is its square. So, in particular, according to Born's interpretation, the quantity that has a physical meaning is your psi star psi, and this is actually the probability density of this particle. If we remember, if we take this infinitesimally small volume and then evaluate this term, this actually gives us the probability of finding the system within this infinitesimally small volume d tau. And if I integrate this d tau over all this function over all the space available to me, that means I go from minus infinite to plus infinite, what the quantity that I get is actually the total probability of finding the system anywhere in the universe. And then we make that equals to 1, and this process is called normalization. By making it to making this integral to 1, we ensure that there exists a finite probability of finding this particle anywhere in the universe. Now, postulate 1 told us everything that we can know about the system is there in the wave function, but they did not tell us that how we can get some information out of it. That was the role of postulate 2. Postulate 2 on the other hand said that if you want to obtain any information about any classical observable, for example, position or momentum of energy or either kinetic energy, potential energy, angular momentum or any other physical observable that classical mechanics has already defined. If you want to know that, then there exists something called operator in quantum mechanics. So, that means for every classical observable there exists a quantum mechanical operator, and this we also carried out, we also discussed the properties of the operator. We discussed how an operator acts on a function. When an operator acts on a function, it gives rise, it changes the function, it gives rise to a new function. We also saw that how we can use the sum rule, product rule in carrying out the operator's action on a state function. We also discussed about linear operator. One particular thing that that I would like to remind you is when an operator acts on a function, often it gives rise to a new function. So, such a function is an ordinary function, but then we also discussed that for a given operator there exists a specific set of functions that actually when you apply the operator on these functions, it does not give rise to a new function, rather it gives rise to the function itself multiplied by a constant. Now, when such criteria is fulfilled, like when an operator acts on a function and the result is still the same function, then we call that this function is a characteristic function of this operator, or the technical term that we used is Eigen Function of this operator. So, a function is an Eigen Function of an operator when, if the operator acts on this function, we get back the function multiplied by a constant, and the constant that we get out is called an eigenvalue. An eigenfunction and eigenvalue, these two quantities are specifically defined with respect to a particular operator. We also saw that the same function can also become an eigenfunction of two different operators. And then we also saw that there could be many different functions that we can define, but only a few of them or some of them would actually be an eigenfunction of this operator. Now, if we combine the knowledge that we have from postulate 1 and postulate 2, we can summarize that postulate 1 tells that psi, the wave function, contains all the information, and postulate 2 tells me that if I want to know any particular information, I should bring that corresponding quantum mechanical operator. But together postulate 1 and postulate 2 did not tell us that if I make the measurement of that classical observable, what is the outcome, that what would be the result that I would get, and that is the purpose that postulate 3 would fulfill. So, we look at now postulate 3. Postulate 3 tells that if you make any measurement of the observable associated with any operator, in this case we are calling this operator A. If you want to know some information about regarding a classical observable that is defined by an operator A, then postulate 3 tells, which is very important, that the only values that will ever be observed are actually the eigenvalues of the operator A. So, therefore, eigenvalues and therefore eigenfunctions are very important in quantum mechanics. Why? Because postulate 3 tells that if you make any measurement corresponding to operator A, the only allowed observable is the eigenvalue of that particular operator A, where in this equation A is the operator, F is the eigenfunction, and it gives to this constant A, which is written in shown in red, this is the eigenvalue, and it gives back action of operator A on this function gives back your function itself. So, this is an eigenvalue equation, and F is the eigenfunction and A is the eigenvalue. Postulate 3 tells that if I make any measurement for corresponding to operator A, the only allowed observables are this eigenvalues A. So, what does it mean? That if I want to make position measurement, I must bring position operator and apply on the state function psi, but the things, the observables, that the outcome of this experiment are predetermined. The outcomes are going to be the eigenvalues of that position operator. Again, if I want to measure the momentum of the system, then I must bring the momentum operator according to postulate 2, apply it on the state function according to postulate 1, and according to postulate 3, the result of this measurement is going to be again the eigenvalues of momentum operator, not any other operator. So, together when we take postulate 1, postulate 2 and postulate 3, we get a complete picture. If I want to make determine a particular classical observable, I must bring the operator corresponding to that observable, apply it on the state function, and the outcome that I would get are going to be the eigenvalues of that particular operator. So, if I make position measurement, the outcomes are position eigenvalues. If I am making momentum measurement, then the outcomes are the eigenvalues of the momentum operator, and so on and so forth. So, therefore, in our discussion, the eigenfunctions and eigenvalues are very crucial. So, we would spend some time in finding out how we can determine the eigenfunctions of different operators. This is what we are going to do next. In the first example, we would look at how we can get the eigenfunctions of linear momentum operator. In this case, this is Px. The operator is given as Px. If you remember the functional form of the operator, minus I h bar, I is the imaginary root, h bar is Planck's constant divided by 2 pi, and the operator is simply d by dx. Now, I want to find out some eigenfunctions of this linear momentum operator. So, I start from this premise that let psi be an eigenfunction. Of course, I do not know what psi is. The purpose of this exercise is to determine psi. So, suppose I say that psi is an eigenfunction of Px operator, and then this is my eigenvalue, the constant, and since psi is an eigenfunction, I am defining it as an eigenfunction. So, therefore, I should get back my psi. So, this is the eigenvalue equation that I must solve to get the wave the eigen function psi and the eigenvalue p. We would continue, we will use the form of the operator. I would now say that there are some quantities with in terms of psi. So, I will collect them all in one side. So, I do this d psi, I keep it and then bring psi from the right hand side and take the remaining quantity to that right hand side. If you see, this is minus 1 divided by I, minus 1 is I square. So, therefore, I square divided by I is just I. So, I can simplify this right hand side by I p h bar dx. Now, what I am going to do is that I am going to integrate both left hand side and right hand side. When I integrate the right hand side, I see I is imaginary root, h bar is Planck's constant, is a constant, and p is also an eigenvalue which is a constant. So, therefore, I am keeping these terms out of my integration. So, I see I have a left hand side integration to carry out, I have a right hand side integration. So, I continue my discussion in here. So, when I do the left hand side integration, I get an ln function, natural logarithm ln psi equals I p by h bar, and when I integrate dx, I simply get x, and I should not forget there will be a constant of integration, and it is a constant, and I am expressing it in terms of a natural logarithmic ln a. So, that does not make much of a difference, except for that you would see how it would help us in simplifying the wave function. So, now I have the left hand side which is ln psi, the right hand side, and now if I want to express psi, then I have a which is coming from this term and e to the power I p divided by h bar x. So, now what I got is that this form of the wave function, this form of the function psi is actually an eigen function of linear momentum operator. What is a here? A is a constant that we still have not determined, but you already know that if I have a wave function, the wave function satisfies certain criteria. For example, it has to be single valued, it has to be square integrable, so that way I can normalize. So, if I normalize this wave function, I will have a normalization constant, and I would use this constant a, any unknown, as my normalization constant. So, this should not bother me. Then I look at the functional form of the eigen function. It is essentially an exponential function, where the exponent is given by I p divided by h bar multiplied by x, x is the variable. Now, and what is the eigenvalue? Of course, the eigenvalue I have defined it as p. So, I have expressed the wave the eigen function in terms of the eigenvalue p. If I look at this term closely, I see that the exponent has I p divided by h bar. Now, the exponent is an imaginary quantity if p is real. So, if p is real, the exponent of this function is imaginary. So, if I have a term as e to the power I theta, then I can always express it as a cosine function and a sine function. And I know what the advantage of cosine and sine function is, that even when x goes to plus infinite or minus infinite, both cosine function and sine function are bound by between plus 1 and minus 1. So, therefore, this wave function will not become infinite at any value of x, as long as p is real. If p is real, this function is a well behaved function. Now, let us see if p is not real, rather p is imaginary. If p is imaginary, we have a problem. What is that? Because if p is imaginary, you would see that I p divided by h bar is essentially minus p by h bar, because I am considering the imaginary part of p and multiplying it with my I, and I am getting a minus. So, this becomes minus p by h bar, where p is actually real, because I have taken the imaginary root out of p. So, now this is real. When I use this expression in the exponent, you would see that my function becomes psi equals a e to the power minus p by divided by h bar x. Now, I have a problem when x goes to minus infinite. When x goes to minus infinite, this exponent becomes infinite, and when the exponent becomes infinite, the wave function becomes infinite. But I know for to have a well behaved wave function, I must ensure that the wave function does not become infinite at any finite interval. So, therefore, p is imaginary is not acceptable. So, the eigenvalues of the linear momentum operator can be any real value between where p goes from minus infinite, p is between minus infinite to plus infinite. Any real value is allowed, but however, imaginary values are not allowed, because if I have eigenvalues imaginary here, the wave function is not well behaved. But what I say is that the eigenvalues of p is are all real quantities. So, therefore, these eigen functions are a set of continuous functions. Please note that when I began, I wanted to have an eigen function, but I actually ended up having many eigen functions, because any value of p, any real value of p I put in, the corresponding function e to the power I p divided by h bar x is an eigen function of the linear momentum operator. So, I have got many eigen functions of this operator. We will continue our discussion and look for the eigen function of another operator, and in this case the operator is LZ operator. LZ is the z component of the angular momentum operator. We have already discussed the angular momentum as r cross p, and if you remember, we in a class in an earlier class we defined this angular momentum in the Cartesian coordinate. But today in this lecture I am redefining this LZ operator in an angular coordinate, and this is d by d phi. So, you can imagine if a particle is going in a circular path. So, the phi is actually the angle that it makes over here. So, phi goes from 0 to 2 pi. Unlike linear momentum, where x went from minus infinite to plus infinite any value, here the coordinate goes, since it is an angular coordinate, it goes from 0 to 2 pi. So, the task in my hand is that to find out the eigen function of this operator. So, I said that okay, this is my I start with the premise that let psi be the eigen function of LZ operator, and let me define the eigen value as a, which is a constant, and I am again getting back my function itself, because this is supposed to be an eigen function of LZ operator. Now, in this equation I put the functional form of LZ operator, and I do the same exercise that I did for linear momentum operator, that I keep the psi part all in one side, and I integrate both left hand side and right hand side. So, I am keeping this constant out of integration. When I do this, I would see ln psi in the left hand side, and in the right hand side I have I a divided h bar phi plus the constant of integration, and if I simplify this, I have psi as a e to the power I now this is the eigen function that I obtained for this LZ operator. Again, we need not worry about a, because we can always normalize this function and get the value of this a. What I have is that in exponent I a divided by h bar into phi. But here the way we have defined our problem, you can see that here the wave function depends on the coordinate, naturally it depends on the coordinate, angular coordinate phi. But here if the particle makes a 2 pi revolution and comes back, the wave function should reproduce itself. So, therefore, we invoke this condition this is another boundary condition, that psi at phi should be psi at phi plus 2 pi, because after making a 2 pi revolution the wave function should reproduce itself. So, when I impose this condition, I see that in the left hand side I have E I h bar phi equals in the right hand side I a divided by h bar phi plus 2 pi. And when I solve the right simplify the right hand side, I see E I h bar phi multiplied by E I Now, when I look at this left hand side and right hand side, the first term in right hand side is essentially the left hand side term. So, therefore, what I am left with this term should be equal to 1. So, I define my A by h bar as a single variable m. So, that my discussion remains a little simpler, and I said I rewrite this equation by telling that I have this condition to fulfill, that I e to the power I m 2 pi is 1. How can I do that? Since this is an exponential function with an imaginary exponent, I can express it in terms of a cosine function plus a sine function. So, these two functions should be 1. When I look at the left hand side and right hand side, I see that the right hand side is completely real, whereas the left hand side has both the real and imaginary part. So, obviously, the imaginary part has to become 0 and the real part has to become 1. And how can I achieve that? It is simple to see, because if I take m as 0 or plus or minus 1 plus or minus 2 and so on and so forth, I can see that the sine function will become 0 for any of these values of m, and the cosine function will become 1 for any of these values of m. So, therefore, what I obtain is that if I want to ensure this condition is satisfied, then I have to have these fixed values or these discrete values of m as the eigenvalue, because my eigenvalue A is defined as m into h bar. So, the eigenvalues, the allowed eigenvalues are 0, plus minus 1 h bar, plus minus 2 h bar, and so on and so forth. So, what I see here, that the angular momentum has again not one, rather many eigenfunctions, but they are not continuous eigenfunctions. That means, I cannot have any function as an eigenfunction of angular momentum operator, rather they follow a particular trend. So, I have this e to the power I a by h, a divided by h bar into phi are the eigenfunctions, where the only allowed values of a are 0, plus minus h bar, plus minus 2 h bar, and so on and so forth. So, therefore, the eigenvalues of angular momentum are not continuous, rather they are discrete. One more thing that you should observe here is that again I wanted to get an eigenfunction of operator Lz, but what I get here is a series of eigenfunctions and eigenvalues of this Lz operator. Just to put the two operators that we discussed in contrast, the linear momentum operator Px and the angular momentum operator Lz, we obtained both of their eigenfunctions. We saw that both of them have eigenfunctions as exponential functions. In one case, in the linear momentum operator case, we saw that the eigenvalues have to be real, rather any real value. They were not discrete, they were continuous set. On the other hand, the angular momentum Lz operators eigenfunctions are discrete. Their eigenvalues are again real, they are plus or minus h bar, plus or minus 2 h bar, and so on and so forth, and they are discrete as well as real. But in both cases, we ended up in getting many eigenfunctions. These are important observations that we would actually use in our future discussion. Now, we will continue our discussion as further. There is an important consequence of postulate 3. Postulate 3 suggested us that if I want to make a measurement corresponding to an operator A, if I want to make a measurement corresponding to operator A, the action of operator A on its eigen function, there is an important consequence to postulate 3. Postulate 3 said that if we make measurement corresponding to an quantum mechanical operator A, the only allowed observables are the eigenvalues of operator A. And since the eigenvalues are the outcome of an experiment, so therefore, since we are going to observe them out of an experiment, so we would assume that A is real. So, if the eigenvalues are real, then I have the following consequence of postulate 3 is that I start from this equation and I multiply f star, the complex conjugate of f function, and integrate this function both in the left hand side as well as in the right hand side. The left hand side I keep, therefore, so in both left hand side and right hand side I multiplied f star, the complex conjugate of the function, and integrated over all the space available to me. So, in the right hand side when I see A is a constant because it is an eigenvalue. So, therefore, within the integral I can rearrange it in the following way, but since A is real, A star is equal to A star is equal to A. So, I replaced A star with A, and then when I look at this A f star, what I obtained is that look at the left hand side and the right hand side. This is a special property of an operator. All those linear operators which satisfy this equality, that is which the left hand side is this and the right hand side is this, we call those operators as Hermitian operator. I can provide a more generic definition of this Hermitian operator by taking not one function, rather two functions f and g. When an operator satisfies this relation for any well behaved function f and g, we call this operator Hermitian operator. As you would see that most of the quantum mechanical operators that we would deal with are going to be Hermitian operator, and this is what we are going to discuss in our next few classes. Thank you for your attention.